Hello, how are you guys? Hello, Lucia. Hello, Ralphie. How are you? Cool, cool, cool. Are you ready for some lead code? We're gonna be doing the biweekly contest that was, the last biweekly, right? Which was 2 weeks ago. Um, I did okay in this contest. I ended up at 124, but yeah, I feel like I could have done much better, but I had a silly bug that cost me on Q4, but no spoilers. Did you do this one? So I guess we can get started. I participated in this one too. Cool. Well, let's see if I can teach you something. Anyways, maybe. Did you get Q4? Here's Q1. You didn't do it, Ralphie? Well, then maybe you can learn something. So let's start with Q1. Sum of largest prime substrings. I did up to Q3. Definitely will learn. Yeah. I want to teach you a technique for Q4 that I think it's pretty simple if you think about it. And I think that if I explain it to you, you will just remember it forever. Sum of large prime substrings. Given a string S, find the sum of the three largest unique prime numbers that can be formed using any of its substrings. Return the sum of the three largest unique primes that can be formed. If fewer than 3 exist, return the sum of all available primes. If no prime exists, return 0. Okay, makes sense. Makes sense that the empty sum would be 0. Note each prime number should be counted only once, even if it appears in multiple substrings. Additionally, when converting a substring to an integer, any leading zeros are ignored. Well, this is all very good. And well, the length of the string is up to 10, right? So here, this boils down to testing for primes, right? Testing if a number is prime. But since the numbers can be pretty big, they can have 10 digits, then we cannot pre-calculate a sieve, right? Because that would be too large of a sieve. So we have to do a different type of prime testing. But we can go over all the indices, right? We do the typical, so we want J to be the end of the subarray exclusive, so that means that we want it to go up to length of n, s, length of s, and so now we have the substring, and we can parse it like this, and this is going to work, right? Because it says that we should ignore leading zeros, and that's how the usual conversion, the usual parsing of integers works. So we don't have to worry about that. And so if the number is prime, then we can add it. Yeah. So we can have a set of numbers. So I guess this is interesting because we could add the numbers before testing for primes, right? Because we want to minimize. So the prime testing is going to be the bottleneck of this code, because there are only so the pairs are very small, right? Because there are only 10 digits here. So maybe we can just add this. Yeah, and well, let's do it this way. It doesn't matter. And then remember that we have a function in Python called the n largest, where we can ask for the 3 largest values, and this should work. And okay, so how do we test if a number is prime? Remember that we can go up to the square root of the number, right? So we can start testing while the numbers. So this is a way. So I know that sometimes people calculate the square root of the number and they use a for loop, but I like to do it this way, so that, because here we're only multiplying, right? Which is a less expensive operation than the square root, right? Because if you have this equation, then you can square both sizes, and then you get this equation, right? So it is equivalent, but here we don't need to call any function, we just multiply. So that's why I prefer to do it this way. And so here, if p divides n, then it means it's not a prime, right? And if we got here, it is a prime, except that we want to avoid the edge case of 0 and 1, right? We want, in that case, we want to give false, to return false, right? So so do you remember why we only have to try up to the square root of the number? This is so the reason is that so you should always remember that divisors come in pairs, right? So if n is divided by a, that means that n can be written as a times some b, right? Some other integer b. So that means that b is also a divisor of n. And they cannot both be greater than the square root of the number. Otherwise, they wouldn't be equal n, right? They would be greater than n. And so if there is if one of them is greater than the square root of n, then the other one has to be smaller than or equal. Well, it has to be smaller than the square root of n. And so if there wasn't one that was less than or equal to the square root of n, then there cannot be one that is greater. So there can't be any. Right? That is the proof of why you can do this faster. And well, and let's think about the time complexity, right? Because here the numbers are up to so 10 to the 10, right? They are less than 10 to the 10 because the biggest number could have all 9s and 9 of them and 10 of them, right? So that would be that it will be one less than this number. So it's actually strictly less. But this algorithm times complexity is the square root of that, right? So, and that would be 10 to the 5th. And so 10 to the 5th, and we're calling this the is prime. We are calling this like square the number of digits, let's say 100 times. I mean, it's less than that, but it is bounded by 100. So that would be 10 to the 7. So even though we didn't use very tight bounds, it's still good enough, right? 10 to the 7 is well, it's right at the limit, but it should be good. We have to return the sum of this. Wasn't too sure about the complexity. Yeah. Cool. So we got accepted. Yeah, so there are a few things to take into account. So yeah, so the analysis that I did. So here, if you want to know how many substrings there are, it's actually 10 times 11 divided by 2, which is 55, right? So then, and also, so I'm saying that is prime. I'm only considering the largest, right? The one that has 10 digits, and it's all 9s. But then only one substring is that long. The others will be shorter, so then that's not a tight bound, right? But anyway, so there are a few tricks that we can use. So first of all, well, one small detail here is, notice that this is actually this part is doing a slice, so it's making a copy of the substring and then it's parsing it as an integer. So it is actually cubic here, but you could avoid that by actually doing the number, well, let's use x, doing something like this, right? And now, I mean, this is not, it's not a big deal because the size is 10, right? But I mean, it's not going to make a difference in this case, but it's good to know the theory, right? In terms of analyzing the time complexity. It's good to know, to be aware that because sometimes when you think about the time complexity, you look at the loops, right? And that's clear, right? You have nested loops, so you multiply, but sometimes you have hidden loops, right? So you have something like this, and one way of thinking about it is to think of how that could be working internally, and you would imagine that internally it's doing another loop, right? So then you can think about it in that way. Anyways, so how can we improve this? So notice that, so one kind of dirty optimization would be, because notice that we only need to care. So I even call this variable p because we only need to test division by primes, right? Because if there's a composite number that divides the number, then it will be composed by primes. So then you will also have primes that divide the number, right? So and so maybe if we pre-calculate the primes, right? Remember that if we do things outside of the class, then they will be executed only once for all the test cases, and they will be fast, right? So here, if we say, if we pre-calculate all the primes that are less than 10 to the 5, then we only need to go over those, right? And we can do that with a sieve, right? So here we say, remember, we start with a table where everything, initially we say everything is a prime, right? Except for, so we mark down 0 and 1. We cross them out because we know they are not primes, and then we start from 2. And if it is a prime, means that it was not crossed out, then we go over all its multiples and we cross them as not primes, right? Because they are multiples of a prime, right? And why do we start from the square of the prime? Well, this is a small optimization. It's not necessary. You don't have to. But so I mean, you could start from 2 times p, right? Which is the first multiple of p. But notice that since 2, assuming 2 is smaller than p, then you already crossed out all the multiples of p, right? So that one should be already crossed out. And then for 3, the same, and so on. So all the multiples of p that have that are multiplied by a factor that is smaller than p should be already crossed out as not prime, right? So you don't have to go over. And here we can say, okay, we append this to our list of primes, and now we have a list of primes, and we can do two things, right? So we already have a table, right? So if n is less than u, then we just return what the table says, right? And if it's not, then we just go over the primes. And again, if p is greater than the square root, we break. And we don't need to do this. And so now we have an optimization. Now it runs in 369. Oh, is this is M. Yeah, so now it's like an order of magnitude, which, yeah, this makes sense. This actually makes a lot of sense, because if you think about, so the prime counting function, so if you, so because before, so if we look about, if you look at how many numbers there are, how many primes there are less than 10 to the, so this function counts how many primes there are less than each number, right? And here you have a table with the powers of 10, right? So the number of primes that are less than 10 to the 5, which is what we computed, is about 10 to the 4, right? So that's a 10%, right? And that fits our numbers, right? Because we in the worst case, we were going over all the numbers less than the square root of n, right? Which could be up to 10 to the 5th. But now we filter out, we only go over the primes which are 10% in that range, right? In number. And we reduced by 10%, so I guess it makes sense. I mean, it's not that simple, because we also have this table, but it fits. All right, so, well, notice that there are better algorithms for tests, for doing prime tests. So this is the most basic one, which is trial division, it's called. And there's another algorithm, a classic algorithm, which is called Miller-Raving, which is a probabilistic algorithm, which tells you it tells you whether the number is probably prime, or if it's definitely not a prime. And it turns out that you do tests with random numbers, and if the number that you're testing fails the test, then it means it's not a prime. But if it passes the test every time, then you can estimate the probability of it being a prime. And it turned out that there are when you're dealing with relatively small numbers, like we're doing here, right? We're dealing with numbers up to 10 to the 10. But I think even if you're dealing with any 64-bit signed number, there are modifications to this algorithm, to the Miller-Rabin algorithm, that choose a base of numbers that they can test with, so that the result becomes deterministic. It's not probabilistic anymore. It tells you whether the number is definitely a prime or if it's definitely not a prime. And we have in the library that I usually recommend, which is the PyRibel library. There is an implementation of its algorithm. If you go into, I don't know if it's in algebra. Yeah, it's prime. Here, it's pretty short, right? I mean, we can use it as a black box. And yeah, PyRibel is great. That's what they have a segment tree implementation that I use all the time, which is pretty cool. So we can replace all this with the isPrime function. So this is obviously pretty easy to use, right? Because the interface is trivial, and yeah, now it's faster, right? And this is what I said, that they have selected, they carefully selected which numbers to make the test with, so that they guarantee the result of the function for numbers in, I think, for 64-bit numbers, which is more than enough for our purposes. So this is cool. So what if we remove the I'm just curious, because what if we remove the duplicates? Here. And then we only test for primes. Yeah, this is probably not going to make a difference, but let me try it. Oh, so yeah. Why is this not working? we're returning. Why do we say? Oh, I see. Yeah. Yeah, it makes sense. Yeah, it makes sense. So yeah, so I think we should do this, and then yeah, because we're not removing duplicates that have they're not exactly the same because they have leading zeros, right? So that's why it's not the same. Cool. Well, it's the same runtime, which makes sense. Cool. So now let's move on to Q2. Find the maximum number of non-intersecting substrings. You're given a string word, return the maximum number of non-intersecting substrings of word that are at least 4 characters long and start and end with the same letter. Okay, and the length is 200,000, right? The usual number that is code for don't do quadratic, right? Don't even think about doing quadratic. Okay, so there are 2 ways of thinking about this problem. So the way I naturally think about this is you can start going from left to right and asking yourself, so you have 2 options, right? If you start from left to right, do I start a substring? So first of all, did you understand the problem? So here, so you have to break down, you have to select substrings, as many substrings as possible that start with a letter and end with the same letter, right? And then, so here you can break it down into 2 substrings, as it says here. But in this example, you happen to select the whole string, right? They cover the whole string, but it doesn't have to. They cannot be overlapping, but they don't have to cover all. You could have letters that are not part of any of the substrings. So the way I was telling you that you can think about this is to say, okay, so I start from left to right, and I say, so I have 2 options, right? The usual take it or leave it, right? So I either start a substring from here, from this place, or I don't, right? If I don't, then I continue. Then I try to do the same thing, but from the next character. But if I start a substring from here, then it's best to end it as soon as I can, right? Of course, if I can end it here, then it's best to end it there, right? Because if I extend it more, then it's not gonna improve my situation to optimize the rest of the selections, right? Or another way to think about it is to say, if I had a longer string that was an optimal solution, I could change this and change it to the shorter one, and it would still be optimal, right? So that means that that's what it's called the exchange argument. That is used for proving the correctness of greedy algorithms. So now it becomes, the problem becomes, how do I find the next A? If I'm here, how do I find the next A? The next A, but remember that we have also this restriction that it has to be at least 4 characters long. So one way to do this, so I usually would, so this is what I'm describing is the P solution, right? But I usually, so the easiest way to implement DP is usually with memoization, right? With a recursion. But here's an exception, because it's easier if we go from right to left and we keep track of the last time we've seen each letter. Then we can do this thing of finding where the next A is easily, right? So that would be bottom-up DP, right? So we want to calculate the max substring starting from every position, including position n, right, which is the empty string. And in that case, that's our base case, right? In that case, we can have 0 math strings, right? And we're gonna go from right to left, and we're gonna keep track of the next occurrence of each letter, right? But with a catch, because we kind of delay this update, right? So when we are at I, we want to, so if we're starting a substring at I, then it means that the substring could end at I plus 3 or more, right? So that means that if I plus 3 is less than n, then the next of word of I plus 3 equals I plus 3, right? And so here we have two options. The mass substrings of I is equal to the mass substrings of I plus 1, which means, okay, we're not going to start a substring here. We're just gonna skip this letter. Or if the next, so if this letter, we've seen it, then we want to find the maximum between what we have and the next word of I plus 1, right? Because this means the next means that that's where our substring ends, right? So we want to start optimizing from the next character, and we want to count this substring in the result, right? And so it should be it. Max substrings. I mean, this name is too long, right? Sorry about that. I don't like this trend of using DP as the name of the DP array. I like to give it more meaning, more descriptive name, but usually I use I rename it to best or something that describes that it is like the optimal value. Good solution. Thank you. Well, but then there's another thing. So this exchange argument that I use, didn't realize we could just keep the next index. Yes, this is pretty handy, because if you do recursion, then, I mean, you can do it, but you have to pre-calculate. I think you have to pre-calculate. You cannot keep track of the next one, right? Right. Yes, that's what I mean. So if you do bisect, you have to have some initial data structure, and then you do, I mean, you don't need to do bisect, right? You can. So I did it in a different way. So here, maybe we can see it here. So this is how I did it with DP, where I mean, it's complicated, but it doesn't require binary search. But I'm creating this data structure where for each value I have a list of indices where it occurred, which is the same that you would have in the bisect solution. But then I also keep track. I also have this other array where I put the index of that value, of that occurrence of the value. And so then I can access, I can have an index inside of this data structure. I can find it, and then I just do increments in that data structure to find the next occurrence, right? Are you following, Lucia? Is it clear? And so you have this loop, but you know that this loop can do at most like 3 iterations, right? Because if the next occurrence of a letter is in the next position, then you skip it and you skip it and you skip it, but at most you would have to skip 3 letters. So then it's not a logarithmic factor. Cool. But then, so it turns out that this argument that I used for this what I call the exchange argument that I used to prove that you always want to stop the substring as soon as possible. You can do a similar argument to prove that a greedy solution would work, because if instead of saying okay, I'm going to start from the first character, just forget about, so instead of saying where I'm going to start, let's think about where I'm going to end. And what you realize is that you want to end as soon as possible, right? It doesn't matter which letter it is. You want to end as soon as possible, because if you find, and you can do the same kind of argument, right? If it turns out that, well, let me get the whiteboard. So maybe you have an A and a B. So I'm saying that here this would be a substring, right? That ends here, and there's no other substring that would end. And you can say that this is optimal because if there was another, so if you didn't choose, if you don't do this greedy choice, let's say you make this choice, right? And you find and this is the optimal solution, right? So you have this thing, and maybe here you have another one and another one and so on, and you get three substrings, and that's the optimal, right? Well, but now you can do the exchange, right? The exchange argument. You can, the first one can be replaced by this one, and you still have 3, right? You're changing this one by this one, and you know that this one ends earlier because that was the greedy choice, and so it will be compatible with everything that this one had after it, right? So that means that the greedy choice will always find an optimal solution. So as soon as we find one substring, we take it. Yes. Do you understand this argument? This is very important, because this is the way to prove all the greedy algorithms. Like this kind of pattern, this kind of exchange arguments. It's like you imagine you have the greedy choice. You imagine that you don't make the greedy choice, and you find an optimal solution, and then you show that you can change it so that you do make the greedy choice and it's still optimal, right? That's the structure of the proof. And so now we can we can remember the index of so we want to know if we can finish if we can finish a substring, right? So what would be, so if x is in idx and I minus idx is greater than or equal to 3, then it means that we can close a substring. So we add it and we clear our dictionary that tracks the last time, the first time that we've seen each letter, right? Well, I think we need to do this because, yeah. So we want to remember the first time that we see each letter. So there are two options. We've seen the current letter, we've seen it, or we haven't seen it. If we haven't seen it, then it's the first time, so we save that index. If we've seen it, we check if the length is right. And if the length is right, that means that we're selecting greedily that that substring. So we start over, we reset all our indices, right? So this should work. And that's it. And it's even faster, is it? Yeah, it's faster. Nice. So it's like 4 times, or yeah, 4 times faster. So and the code is simpler, I think. So I mean, but yeah. So this is so. During the contest, I actually did the DP solution. But the reason is more strategic, because so if you have a lot of practice with the P, and you come up with the DP idea quickly, sometimes it's a good strategy to just go for it instead of thinking whether the some greedy solution would also work, right? Because the greedy solution requires proof, right? So if it's not immediate to you that it would work, yeah, it's like I think during the contest, like when I saw that the DP solution would work, it's like I stopped thinking about anything else and about something greedy. I just went over and implemented it, right? And so but many people went for the greedy solution. Makes sense. I went for DP2. Yeah. I guess the problem with the P is that if you don't get, so if you don't find this implementation idea, this idea of doing it bottom up, then the implementation is a little more complicated, and in that case it might pay off to think about the greedy, to spend a little time thinking about the greedy, because it turns out that the code is simpler, right? So it might pay off, but with this implementation is pretty short. So, and if you have practice with the P, you can implement it pretty quickly. It's also a little weird that, so usually for problems when a DP solution works, the greedy solution doesn't work. At least in my experience, that's usually the case. So anyways, let's move on to question 3. Number of ways to assign edge weights 1. Okay, so this whole paragraph is saying that we're given an undirected tree with n nodes. This is just standard speak for we're giving you the edges and so on. I mean, you don't have to read it word by word. Initially, all edges have a weight of 0. You must assign each edge a weight of either 1 or 2. The cost of a path between any two nodes, U and B, is the total weight of all edges in the path connecting them. Select any one node X at the maximum depth. Return the number of ways to assign edge weights in the path from node 1 to node X, such that its total cost is odd. And returning modulo. Okay, so modulo, let's write this down so we don't forget. So notice that there's something really weird about this description, which is it says, so if you read it superficially, it says select any node and then calculate something about that node and return that. So, but you say, but how? But wouldn't it return if I calculate something of the node? Wouldn't it matter which one I choose, right? I mean, they say it's a maximum depth, right? So this is implying that it doesn't matter which one you choose, as long as it has maximum depth, it should have the same number of ways, right? So, I mean, if you think about the property that you're asked to calculate, then it makes sense that you can see that it's true, but a priori it's kind of weird the way it's phrased. Because, so yes, you have to realize, so the only thing that matters is the length of the path, right? The length of the path from the root to the node at maximum depth, that's going to be the height of the tree, right? So this is kind of a fake problem, because they're telling you, they're basically telling you, okay, calculate the height of this tree and then calculate something about that number, right? So apply some function to that number, right? Some combinatorics. But the tree is just an excuse to give you the input of that function, right? So we can calculate the depth of the tree with the usual way to do this. You would create the the adjacency lists, and then you go over the edges. Yeah, notice that it's weird that the edges are, the nodes are 1 based. They usually don't do this in LeetCode. For some reason they chose. So I like to have everything 0 based, so let's do this. So this is the usual code, and now what I like to do to calculate the depth is to do a BFS. So we could have a queue which starts at node 0, and the initial depth is 0, right? And so we go over the queue and we go over the adjacent nodes. Yeah, and we also want to know the parent, right? So this is U, and this is the depth, and this is the parent of U. And so if B is not the parent, right? If we don't want to go back, then we want to append B with depth +1 and with U as the parent, and we want to calculate the max depth. So the max depth is the maximum between the max depth and D, the depth. And so now we have our max depth, right? So we want to calculate. This is kind of an easy Q3, right? I think this is easier than Q2. So notice that. So remember. So this is important, right? You want to. So notice that now we have a number, right? We have this number, and the tree is gone, right? So we should get the tree out of our minds and think about this new problem that doesn't have anything to do with trees, right? So the new problem is we have. So we have, let's say that this number, D, let's call it D. I mean, well, maybe D is not the best name, because I want you to forget about the tree, and D comes from depth. So let's call it N. And if N is 4, then it means that we want to add 4 numbers. And we want this to be odd. Is it that? Yes, the total cost is odd. We want this to be odd, which means is congruent to 1 mod 2, right? That's what it means. And so and we can put a 1 or a 2 here, a 1 or a 2 here, 1 or 2, 1 or 2, right? So one thing that you can notice, so let's say that, I don't know, that you put 1 here, 1 here, and 1 here, and now you have this, right? So is it, do you have a choice for this one, for the last one? Well, no, you don't have a choice, right? Because this is odd, right? So it's 1, and you want this, which is odd, to be added to this fourth number, and so that it's still odd. So you're forced to put a 2, right, to make it odd. And so if we assign the first 3 numbers, the last one is determined, right? And it doesn't matter which one we choose, right? If you choose 1, 1, and 2, then this is even, and so this has to be odd, so it has to be 1, right? So it's already determined, right? So basically we can choose, so what I'm proving here is that we can choose anything of the first 3 numbers, the third 3 numbers, we can choose anything between 1 or 2. And then the fourth one, we don't have a choice, it's forced. And so that means, right, and so that means that we have 2 options for the first one, 2 options for the second one, 2 options for the third one. We multiply them together, we have 8 options, right? So it's 2 to the 3, and in general it's 2 to the n minus 1, right? Because this is going to work for any number n. So basically, once we have assigned all the numbers except the last one, if the sum is odd, then we're forced to put a 2. If the sum is even, then we're forced to put a 1, right? So it's the same idea for any n. And so that means that we need to calculate 2 to the n minus 1. And so, and there is a function, so you might be tempted to do this, but this is not, so there is a function in Python that calculates powers, and well, this is math dev, that calculates powers that already that also accepts a mod function. So and this is going to be more efficient, right? Because this number, this power of 2 could be a huge number, right? And so if you do it this way, it will calculate this huge number with a lot of digits, and then it will only get the it will mod it, right? But if you do it this way, it will be modding before calculating the whole number, so the numbers will be small, right? So it will be faster. And it seems like it works. And it does. Cool. And now for the last one, Q4. So it turns out that Q4 is the same as Q3, but yeah, it's not that hard, right? It's the same as Q3, but instead of doing it for, so you still have to do the same thing of counting the number of ways of assigning weights, that could be 1 or 2 to the edges in a path. But now, instead of the path being the root and a maximum depth node, it's any pair of nodes. And they give you queries, and for each query is a pair of nodes, and you basically have to calculate the distance between any pair of nodes quickly. And then we can use the formula that we derived for Q3, right? So this boils down to, this reduces to finding the distance between pairs of, so responding queries of this distance queries, right? Distance queries in a tree, right? And so there is this can be solved with a technique that is called it's called binary lifting. So the idea, so if we have a tree, so let's say that we have this node U and this node B, right? And we want to find the distance between them, right? So paths on trees always go through what is called the LCA, which is stands for the lowest common ancestor, right? So here, so the ancestors of B are B itself, so this node, and this node, and the ancestors of U are this node, and this node. So this one here is the lowest common ancestor, right? And so the path goes from B to the LCA. So notice that if we knew the LCA, then we can calculate the length, the distance from U to the LCA, and then from the LCA to B, and that would give us the distance, right? And that would be, so if we know the depth, right? The depth, which is the distance from the root to every node, if we have the depth of U minus the depth of the LCA, that is going to give us this distance, and then the depth of B minus the depth of the LCA. That's going to give us what we're looking for, right? So now we reduce this. So how do we get the LCA quickly? That is the question. So the idea is to do, so the basic idea is, so here, how do we find the LCA? We can even, let's make it more complicated. So notice that, so since we already, we can pre-calculate the depths of the nodes, and we're trying to find the LCA of U and B, here notice that the depth of U is greater than the depth of B. So we could, if we move up to the parent until we get to the same level, right? Until the depth is not greater, is equal, right? So we could do something like this, right? While the depth of U is greater than the depth of B, then U equals the parent of U, right? So now they are both at the same level. I mean, there is an edge case where the LCA is B, right? And in that case, you're done, right? But let's say you're not done. Then and notice that this is a slow algorithm, right? Because if we're going one by one, this could be the whole tree, right? And so this wouldn't be fast enough. But I'm illustrating the idea. Then we're gonna find a way. This binary lifting is gonna allow us to make jumps, so that this becomes quickly. We can do this quickly, right? And so, but okay. So why do we put them in the same depth? Well, the reason is that then if we go up with both of them and we maintain this invariant, we maintain this invariant that they are always at the same depth, then when they reach the lowest common ancestor, they will be at the same node. If they are at the lowest common ancestor, or not the lowest, so at any common ancestor, then they will be at exactly the same node, right? So we can use that information to find that place, right? So now let's go to the, how do we do this quickly? How do we do this quickly? Well, we can use this technique called, eventually they'll reach the same parent. Yes. And so how do we do this quickly? Well, we can use this technique called binary lifting, where we pre-calculate how to make jumps. So instead of doing just the jump to my parent, right? So when I calculate that parent of u, well, what if I calculated a list of the ancestor k of u, where k is a power of 2, right? So if k equals 0, that means that I'm moving up up 2 to the k times, right? So if we could calculate this, then we could do this quickly, because we know that the difference of depth is depth of u minus depth of b. And so now we know exactly how many times we need to move up, but we can always decompose numbers into powers of 2, right? That's what writing numbers in base 2. So if this numbers happens to be 10, then we can write it as 2 to the 3 plus 2 to the 1, and we can use this table to make a jump with k3 and a jump with k1, right? And we know that there is a logarithmic number of powers of 2, and so we can decompose any jump that we need into a small numbers of jumps of powers of 2, and so we can do that jump in logarithmic time, right? Yes, the second part is a little more complicated. I'm gonna explain it when afterwards, but first I wanna finish this. So how do we calculate this table? So we want to calculate this table. So notice that if we go from k from 0 up to some number, that we're gonna see how much this limit has to be. So we want to go up to a number that guarantees that we're gonna reach the root, right? Always. So notice that powers of 2 are recursive in a sense, right? So if you want to do a jump of size 2, then that consists of 2 jumps of size 1, right? And if you want to do a jump of size 4, then that would consist of 2 jumps of size 2, right? So that means that we can calculate this recursively. Well, recursively in the sense that we can do dp, right? But we can say the ancestor of k at u is equal to the ancestor of k minus 1, which means that is half the jump, right? And since we're calculating from 0 on up, that means that when we're trying to calculate k, we already have k minus 1. But instead of doing the second jump from u, we do the second jump from the ancestor of k minus 1, of size k minus 1. We want to half the jump from u. So this will be the first jump, right? We jump from u 2 to the k minus 1. That's the length of the jump, and this is the node that we're at. We can call it b if we want to. When we make one jump, we are at b, and so now we use the ancestor table again, but now from b, and we make another jump of k minus 1, right? And so this is the recurrence that we can use. So we have to do, so this is going to be the same, right? And now we want to create the ancestor table. Well, notice that, so the number of nodes is up to 10 to the 5th, right? So that means that we can have a jump. So the maximum jump that we would need to reach the root will be 10 to the 5 minus 1, right? So we have to think about what power of 2, what power of 2 gets there. So that means that 2 to the 16 doesn't quite get there. You have to go, it would be 10 to the 17, right? So 2 to the 17, it goes over, right? So that guarantees, if we do 10 to the 16, then we're not guaranteed to get to the root in the edge cases. But with 17, we are guaranteed, right? So that means that our table has to have size 18, so that it goes up to 17 inclusive, right? I call that log because it's the logarithm of the size of the approximately. And so here we're going to create this table, and we're going to assign 0 initially, because that means that, so we want the root, which is the node 0, to have ancestor with k0, so which means that the parent is going to be itself, right? We want, because that's going to make that when we jump over the end of the tree, we'll still want to end up at the root, right? we don't want to go out of the tree. So now we're going to do a BFS like we did before. And we are going to go through this, and we want this to be different than the parent of U well, but we also want to calculate the depth, right? That's something that we need. So here we want the depth of B to be the depth of U plus 1, right? So now we have all the depths, and we have the ancestors for K0, which means the parents. But now we can use our recurrence, right? We want, let's call it E of exponent. So 0 is already covered. Is already, oh, sorry, we need to do this. Ancestor, yeah, you're right. Ancestor of B equals U, right? So 0 is already covered. So now we start from 1 till the end, and then we go over all the nodes. And now we write down what we wrote in the whiteboard, right? We want the ancestor exponent U E of U equals the ancestor exponent E minus 1 at the ancestor of E minus 1 of U, right? So now we have our binary lifting table ready. So we can create the function for getting the LCA, right? So how do we do this? So remember that we assumed that the depth of U wasn't less than B. So usually in algorithms you can make a swap. So if that's not true, so you want to assume that the depth of U is greater than or equal to B. So if that's not true, then you swap them, right? This is how you swap in Python. You don't need a temporary variable. So now, wait, this is depth. Right, so now we know that the depth of U is greater than the depth of B. So we calculate this diff. Right? I guess we can always add an assertion, right? And so now we want to convert diff into base 2, right? And this is the usual algorithm where you so here is mod 2, and then you divide by 2, right? This is the usual, right? This is yeah. And so we want to get the ancestor E, right? I guess, so there's another way of doing this. Well, I guess this is fine. I mean, you can use a for loop. So I don't like this that much. The fact that we have to have two variables. But the advantage of this is that you stop early, I guess. Anyways, so now we know that the def of U is equal to the def of B, right? So now there's a special case, right? Maybe this is already the LCA, right? Now, if B was the LCA, then now they are the same, and you return that, right? So that is one option. No condom Chris, how are you? Template copy paste problem, yeah. So many people got the Q3 observation for this contest, yeah. To see you back. Thank you, man. Thank you. Yes, I'm back. I already did a stream this week. This is my second one, and I'm planning, so tomorrow there's double contest, and I'm planning to do a stream of both of them, so stay tuned. Let's go, yeah. I'll ask for the link later and add it to my live. Yeah. Yeah, I actually added. So in this contest, I didn't have it. And that's why I wasted some time implementing this. And I had a very silly bug, a typo. And that's why I got a wrong answer. And I spent like 10 minutes debugging. So I think I could have done much better in this contest, but anyways, that's okay. Okay, so now our situation is that so we know that U and B are not equal, but if we jump to the LCA or to any common ancestor, then they will be equal, right? So it's like so we can think about doing a binary search. So we can think of going from the largest jump that we can do, right? The largest jump, so there are two options, right? If we do this jump, are they equal when we do this jump? That's the question, right? But if they are not, if they are equal, it's because we reach the lowest we're at the lowest common ancestor or higher. But if we don't, then it is safe to make this jump, right? So we should make this jump, and we're gonna keep we are going to maintain our invariant that U and B are different. But I claim that at the end, so this is as much as we can jump without this is we did the largest jump that we can do without they being equal, right? So then their parent, once we ended this loop, their parent has to be equal, and so it's the lowest common ancestor. Okay, and so we're done. And so now we can solve the queries, right? So we calculate the LCA. And we return the depth of U plus the depth of V minus 2 times the depth of W. Right? Oh no. Oh, we need to yeah, what am I doing? This is so yeah, I forgot about the other part of the problem. So we want the power, how was this? 2 to this minus 1, right? So this is the yeah, I forgot. So this is the distance, and so now we want the 2 to the distance minus 1, right? Yeah. Well, it's their if they are to blame, because this is it's kind of a silly and now what? Oh, there's a special case, because the distance could be 0, right? If they are the same node, the distance could be 0, and then we're calculating 2 to the minus 1, which is not what we want. Because if the distance is 0, then the sum is 0, and you cannot make it odd. So then the ways of making it odd are 0, right? Nice. Cool. 1 second. All right. So yeah, so it's I took I took the idea of forgetting about of separating the problems too seriously, and then when I had to remember what the actual problem was, I forgot. Pretty cool that you wrote the LCA from scratch. Yeah, thank you. Yeah, I think it's not once you understand this and you make you think through the idea, it's pretty simple. the link. Yeah, I'm gonna. I mean, well, let me share it. But remember that I add all the links in the. I add all the links in the description of the YouTube video. I'm gonna export it. I export it afterwards, and I'm just gonna add it to my Live Now before I forget. Yeah, good. Nice. Yep. Yeah, there was a so they are repeating. So in lead code sometimes have like themes that they repeat, and in the previous contest there was also a contest where you needed to calculate the LCA. So, but I couldn't. I think I couldn't participate in that contest, but I did. I absolved it, and I did implement the LCA. But I was rusty because I hadn't implemented it in a while. And even though I did not add it to my library, the practice of implementing it was handy during this contest. Even though so I had this silly bug, but the rest of I coded it pretty quickly, right? So in the previous one, I had a more serious bug, not a typo. And then I think I had a problem in here. I think I got confused. But now after this, I did add it to my library, so now I'm prepared. If it comes for a third time, well, I mean, it didn't come in the last contest, but if it comes again, I'm ready, and you're ready too. So that's great. Cool. So that's all I got. Thank you for watching, and remember to join me on Discord, and remember to participate in tomorrow's contests. There are 2 contests tomorrow, and remember, I'm gonna be doing them, and I'm gonna investigate the problems after the contest, trying to find as many ideas as I can, and then I'm gonna be doing streams to teach you about it. So stay tuned. Okay, bye bye.